So before I prove the Carne-Varopoulos bound in 20 minutes, I need to just declare two lemmas, and from these lemmas we can prove the Carne-Varopoulos bound very easily. The first lemma that you need in order to prove the Carne-Varopoulos bound is just the probability that your simple random walk is greater than d is upper bounded by e to the d squared over 2n, and also we want to prove that lambda to the r, if you sum over r, which is in z, the probability that Sn is r is equal to 2 to the minus n summation over r lambda to the 2r minus n choose r. So we are, if you just fix n, your random walk could go here and could be here, could be at n, it is at this point. It could go several ways. So there are many different configurations in your filtrations. So there are many combinations, and that in your path space. Another important lemma that we need to prove the Carne-Varopoulos bound is that we want to try the polynomials to each other in a very interesting way. So if q of t is sum of AR, TR, be a polynomial with q of t is just bounded by 1 for t in minus 1 and 1. So if r is q of p, so if you just replace your t, which is a scalar, by a matrix, which is now we replace it by matrix. We use this trick in all matrix analysis, random matrices, and everywhere. So we will notice that this becomes this. But the lemma says that if this happens, then the norm of the L2 norm of RF is bounded by L2 norm of F. The proof is very beautiful, and we can learn from the proof. So when gamma, your graph, is finite, using just use spectral representation that I've said several times. The spectral representation says that we just write it as at this, where this is the eigenvalue of P, of matrix P. This is the eigenvector of P. So we can say that RF is equal to R from 0 to K, ARPRF, which is equal to R from 0 to K, AR I from 1 to K, F and Phi. So this goes to the R, and what remains is that it becomes Q of rho I, but this is less than 1. And the inner product of phi and phi, so projected on phi. And let's see what happens. So what we can observe easily is that the summation over I, Q rho I squared, phi and phi squared, is bounded by I from 1 to n, f and phi squared, which is just the L2 norm. So let's talk about another theorem. I cannot prove it because we don't have time. So another lemma is that it is the Chebyshev polynomial. Hk of t is it is very popular, I minus t squared plus 1/2 t minus I, 1 minus t2, 1/2 to the k. So the lemma says that if for each k, your Chebyshev polynomial is a real polynomial in t of degree k, and hk of t is bounded by 1, then we can say an important and beautiful thing. That's t to the n, this beautiful polynomial, is related to the probability that your random walk times your Chebyshev polynomial at t. So we have related this polynomial to a random walk. And our trick in the proof of that Carne Varopoulos bound is just set this scalar, set it to a matrix, and you will see how the trick will create a beautiful thing. So instead of proving this, I just want to declare the Carne Varopoulos bound and prove it. So the bound is that Pn x and y is bounded by 2 over mu x mu y to the 1/2 e to the minus the distance between x and y plays an important role. This is very beautiful. So what is the proof of that? Let's go and prove this beautiful theorem. So we want to calculate. What do we want to calculate? We want to calculate Pn of x and y. So instead of Pn and x and y, I use the popular trick. It is just the inner product of this and this. And I tell you, you may have seen it several times, that this fi is just 1 over xi. For example, here is 1. x1 of x mu x1 minus half. The same thing for this. This is just 1 over x2. This is the indicator function of x2, evaluated of x, mu of x2. So we have related the matrix to just an entry of that by this inner product. And from here to here, we just use that Chebyshev relationship, because this is just equal to the probability over the probability that Sn to the k. Remember how I related that? So let me recall how I used that polynomial. So as I said, Tn is equal to the probability that random walk is equal to k, h of k of t. So I have written Tn to be, I have related this Pn of x and y to the inner product of h of k of matrix P times F2. Until here, everything is beautiful. So instead of summation over k over z, we use a simple observation that many of them are just 0. So what we are left with is just they are greater than r, the probability that Sn becomes k, and essentially the same thing here. We are just summing non-zero part. Why? Because this is 0, because this term is 0 for if k is less than r. If you observe this, you know that y from k, we go to just concentrate on k greater than r, because otherwise it's just 0. So this is what we are left with. And this is bounded by the probability that your random walk equal to k L2 norm of F1 times your Chebyshev polynomial at k evaluated at matrix P, F2 again. And then we use that lemma. If you remember, I told you that if it is Q of P, and then that lemma that I told you, it is bounded by L2 norm of that. Now you use that lemma here, because this term is essentially less than 1. So what we are left in is upper bounded by the probability that Sn equal to K, K over K greater than R, because otherwise it's just 0. And then this is the probability that your random walk is greater than R. And you know Houghton inequality, you know all of those beautiful inequalities, and finally you reach your goal, which is minus R squared divided by 2n. So combine it with this thing that I told you, we can complete the proof. So you see how beautiful it is. So we have proved the Carne-Varopoulos bound. But this is just the beginning of modern mathematics. These are some kind of isoperimetric relationship, I call it, because, as I told you, random walk on weighted graph, this is my motivation that I cannot go to bed. Random walk on weighted graph is so complicated. The analysis of that is so complicated. Unless you use, for example, you restricted it to planar graph, you restricted to infinite tree, something that is very restricted, some Cayley graph, some what do you know that Indian mathematician Ramanayov expanders. So some special graphs. If you restrict to, for example, a Ramanujan graph, Ramanujan expander. So if you restrict yourself to some restricted family of graph, analysis is easy. So here is random walk on something that we love, which is ZD. D equal to 1 is like this. Somebody goes there, somebody goes left, right. Z2 is just this, and it is recurrent. And in Z D equal greater than 0, it becomes dangerous because it may never come back to 0. If it goes to infinity, it may never come back. So this becomes still an open problem identifying this. But anyway, for D equal to 1 and 2, we know a lot about these random walks on these simple lattices. So we just need to relate this P, this matrix P, or even P to the n, to something that we know, for example, random walk Sn. We know about Spitzer, if you know Spitzer theory, how the maximal process is related to that. So if this is your dual process, this is the idea that I am giving to you, is that if this is the dual process and your dual process is much easier than your primary complicated process, by duality, what you observe here, you can do, we can come back, always we can come back and we conclude for the primary problem. Just like another meta idea that we use in electrical engineering, or image processing, or anything that to do with transformation, such as Fourier transformation. For example, here the space of function is very complicated, but you use a discrete Fourier transform or a continuous Fourier transform to go in a space that is lovely, that is bounded, so the spectrum is bounded, and we can understand these compact supported functions easily, and then we come back to the original by just inverse Fourier transform or inverse Laplacian or inverse your favorite transform to get ideas from to understand the original problem. And there is an important thing called have you heard the shape of the drum? So all of these are related to harmonic analysis as well. So about harmonic analysis, you need to know about superharmonic functions, Laplacian, harmonic functions, superharmonic functions, subharmonic functions, submartingale, supermartingale, martingale. So you can either do classical stuff like you do in PDE, or you can be just use probabilistic, which is much better than classical approach. We just use martingale. So for any harmonic function, you have a martingale. And even if you use optional sampling theorem, you can evaluate it at some stopping times. And for the superharmonic functions, we have super martingale. We can use the properties of that. For example, in Ito calculus, in stochastic differential equations, these are fantastic things to do those integration, still G integration, any kind of integration. And there's most of the times, unit measure theory as well. But if you use some concepts, then you can get around and even just do a little measure theory. We don't need to deal with very complicated measure theory. But here, for example, is submartingale. And all of these are, I call it theory of dupe, because dupe was interested in probabilistic potential theory. A very big yellow book, very thick book. And Dupe was a mathematician that has inspired many others. And one of the important things is that he tried to relate the classical things, like a simple mean value property of harmonic functions, to something which is much more general, like the probabilistic view of potential theory. And in potential theory, for example, superharmonic functions, they call it even excessive functions. And I will talk about generating functions. Generating functions. For example, you may know probabilistic generating functions. You may know characteristics of a random variable. All of those things are essential in order, if you want to understand the distribution of a random variable and understand the functional central limit theorem of a random process, a stochastic process. So these ideas are very essential in effective theory of to develop theory of effective resistance and those things. I've also seen that people relate effective resistance to the Gaussian. For example, the Gaussian of for example, they relate that the effective resistance between X and Y to be, and here we're related to a Gaussian field, the free Gaussian or a Gaussian process, because they're related to the expectation of nu of X minus nu of Y, and they even use it for to obtain cover time. I think Yuval Perez was the person who was working on this. Even James Lee was very interested in relating your effective resistance to the Gaussian process. So there are many ways to. What I want to say is that there are many ways to relate your complex primary process, which is very complicated, to a dual process. Your dual process could be anything. It could be a Gaussian process, Markov random field. It could be a a random walk on lattice, something we understand it very well. Dual process could be evolving set of Yuval-Perez, or weighted biased evolving set of Yuval-Perez. So dual